A spar is a beam that is placed span-wise in aircraft wings, acting as a skeleton used to support loads carried by the wings through bending and torsion. Our objective was to design, build, and test the wing spar for a simple wing structure to meet structural performance requirements and size constraints, following the key steps in engineering design. For this activity, the spar was idealized as a cantilever beam, supporting an aircraft mast that acts as a point load at the wingtip. Excel showed the optimum design of the spar would be wider at the root than the tip, to support greater bending moment whilst not twisting more than 3 degrees per Newton meter acting on it. Our initial design consisted of uniform cross-section beams and were drawn onto paper. However, to come up with dimensions that would satisfy the structural requirements, we used an Excel spreadsheet. This allowed us to input design constraints. Foam board sheets to be used for the wing structure were 5mm thick, therefore to increase thickness we did so in increments of 5mm. Whilst ensuring our design satisfied the structural requirements, the spreadsheet was used to check that the design fit inside the wing, with the spar located at 25% of the chord. Designs with a larger height and width had a lower direct stress but were too large to fit in the wing. This was an example of a trade-off we had to make in the design process. Based on the Excel spreadsheet, Design 1 met all the structural and size requirements, therefore we were ready to test it further and begin to look at optimizing the mass. We used SolidWorks to make the 3D model of the wing. It was required to make an assembly of the foam board wing consisting of the spar, ribs, trailing and leading edge components. We assumed the load of the aircraft was to be supported by the spar only, therefore the only constraint faced with the design of the secondary structure was ensuring the size of the spar fit into the geometry of the wing provided in the brief. Although preferred configuration was making a tapered spar for the 3D model, but it may be too challenging as each rib would be different from one another. Therefore, sticking to a uniform cross-section beam, we made a 2-scale model. One thing we considered was attached to the leading and trailing edges, whilst keeping a thickness of 5mm. Using the simulation tool in SolidWorks, we could demonstrate further how the tip experiences the least stress due to the maximum bending moment at the root. Using this simulation, we tested our original rectangular spar, 2 spars with the same cross-section with holes that cut out from the tip to reduce mass, as well as a tapered spar. The simulation showed that the spar with no holes experienced the least deflection whilst having the greatest mass, and vice versa for the tapered beam. It was concluded that the lower the mass of the spar, the greater the deflection. Therefore, from the simulation, the spar with 4 holes performed best. We tested the spars which performed best in the simulation in the lab. The SolidWorks, Excel and lab experiments consistently showed that the spar with no holes deflected the least and the spar with 4 holes would deflect slightly more. We also carried out a torsional test to compare the results from the Excel and CAD simulation. Upon testing the spar with no holes, the measured torsional compliance was 1 degree, whereas the spar with 4 holes had a torsional compliance of 3 degrees. As the angle deflected in the lab by the 4-hole beam was within structural requirements, whilst minimizing mass, the 4-hole beam was chosen to be in the final wing model. We learned the contribution of different ways to test designs, as some methods could not be used for certain designs. The use of pen and paper as well as Excel allowed us to conceptualize our ideas with minimal time. However, the SolidWorks simulation allowed us to conduct more advanced analysis that couldn't be done in the lab or through Excel.